Inside a black hole lies a mystery. What happens at its center? The same mystery applies to the Big Bang. Einstein's theory of gravity seems to give way, predicting the existence of a singularity, a point of infinite density, curvature, and pressure. When the entire observable universe is squeezed into a space far smaller than an atom, new physics is needed, taking account of both gravity and the strange microscopic world of the quantum. We need a quantum theory of gravity. One of the leading candidates is loop quantum gravity. In this film, we'll tell the story of this theory, how it was developed, and how it might finally be tested. We'll meet some of the key players in the field, from the younger generation of scientists to the founders of the field, including Abhay Ashtekar, who even as a teenager found a mistake in a textbook written by Nobel Prize winner Richard Feynman.
Well, being a little bit brash at that time, I decided to write to Feynman. And I didn't really expect that he would reply, but I was a bit surprised that he did. And he said something like, congratulations, the book was wrong, you're right. But then he also ended basically by saying, you can rely on yourself. I think this was kind of a subtle note saying I shouldn't keep writing such letters to him.
A passion for astronomy was there since I was a child. The first book I remember I picked up myself from a bookstore was about astronomy. And the other one was about cats. So I was a cat and star person.
I count myself fortunate for having read and spent time in going intellectually in various directions. Then I got completely enamored in physics. I sort of got in love with physics. I remember distinctively at some point I said, this is so beautiful, maybe I want to do that in life.
When I was very young, I wanted to be a researcher in biology because I was really interested in animals, plants, and all the living world. And then I switched to physics. I don't really know why, probably because it was even stranger to me. It was a desire to go and to see what cannot be immediately seen.
I got interested in physics through architecture. I got interested in architecture because of Buckminster Fuller, who was the great visionary and ecologist and engineer and architect. So I thought that I would design greenhouses and swimming pool covers and second homes and things like that out of geodesic domes. But I had this idea, and I'd written a code, a program, which could stretch a geodesic dome and basically make a triangulation out of any curved surface. Little did I know that that would be what I would be actually doing in science years later.
The realization that there was a problem with quantum gravity is by Einstein. Immediately after having done his theory, general relativity, he wrote the main equations of general relativity in 1915, and 1 year later, in 1916, he writes this paper saying, well, actually, by the way, this cannot be the end of the story because there is quantum theory. Matvei Bronstein, a young physicist, a friend of Landau, who, in my opinion, is the first one who had full clarity about the deepness, the depth of this problem.
So in the beginning, particularly people like Feynman and Bryce DeWitt, tried to incorporate, tried to generalize the methods that had been used in quantum electrodynamics to gravity.
It's quite usual in physics that we end up with infinite quantities. The problem is that nature doesn't like infinity. So renormalization is a technique that was invented to get rid of those infinities. And it works very well, and it leads to measurable results.
But for gravity, it turned out that the theory is not renormalizable, and therefore these ideas ultimately had a real roadblock.
Usual physics is done with space and time, and the physics happens in space and in time, so to say. The space is there, is given. While in quantum gravity, it's space itself that becomes a quantum object. So the usual technique of quantum field theory don't work. And I guess the breakthrough in the 60s was by John Wheeler and Bryce DeWitt, who wrote with this very famous equation, which is the Wheeler-DeWitt equation.
The Wheeler-DeWitt equation was an equation invented by Bryce DeWitt, which is like the dynamical equation of quantum gravity. It's analogous to the Schrödinger equation of quantum mechanics.
Wheeler-DeWitt equation is not well defined mathematically, but full of ideas. And people at the time, especially John Wheeler, produced a lot of the intuition that later on became the driving force for quantum gravity.
John Wheeler in particular was much more interested in also issues having to do with singularities of general relativity. He often emphasized an analogy with hydrogen atom. See, for the hydrogen atom, if you ask for what is the lowest energy available to it, then in classical theory, that lowest energy is minus infinity. But that is an artifact of ignoring quantum physics. So Wheeler was convinced that singularities of general relativity are really artifacts of ignoring quantum effects.
He had this picture. If you fly over an ocean at very high altitude, you see the ocean as a flat surface. That's how we see the geometry at our scale. But if you come down, you see the waves, and then you see the foam over the waves, and that's how the short-scale structural space-time should look like.
I started thinking about working on quantum gravity as a graduate student. In fact, the very first paper I wrote was a review paper because I wanted to learn all about it. And so it was a review paper I wrote with my advisor, Bob Garrosh.
I chose to go to Harvard where there was no interest in quantum gravity, but there was great mastery of the standard model. And I had this idea that maybe the mathematical and physical techniques that could guide into understanding QCD and the standard model would be useful for quantum gravity.
I decided that this was a worthwhile problem to get into. You know, when you're 20s, you're all the courage of the world. So I said, okay, that's what I want to do.
To gauge means to measure. And the gauge theory is a theory where the degrees of freedom, the things that vary, are fields that tell you how to bring systems to the observer in order to measure them. I heard a talk by Ken Wilson, and this was he introduced a revolutionary technique to understand the quantization, or how these gauge fields describe quantum mechanically. And the important thing that he discovered is that they make lines or tubes of flux which can be quantized into carrying discrete amounts of flux of the charge.
First person I went to see is Chris Isham, the person whose review papers had pushed me into the field. So I went to London. I remember distinctively Chris telling me that, in fact, a few days before I left, he told me that there was in America this young Indian, Abhay Ashtekar, who apparently had made a change of variables in general relativity who might simplify the problem somehow. So I got interested. I wrote to Ashtekar, and I went to see him in Syracuse. And the work of Abhay was based on a previous work by Amitabh Sen, who had rewritten general relativity, classical general relativity, so Einstein theory, in terms of some variable, a connection instead of a metric.
What are metrics? Well, they define distances between 2 points, or they define angles between 2 vectors. They define light cones at every point, so they give a meaning of causality. And therefore, the metric appear in every differential equation we write down in general relativity. So these were always regarded as a fundamental object. But it turns out that all other theories of all other basic forces of nature, the electromagnetic force, the weak force, and the strong force, they are really based on connections rather than metrics.
You know, in physics, we are interested in the way things change, and it is encoded in the concept of a derivative. But it's complicated to define a derivative in a curved space. So basically, the connection is here to define properly a derivative that is a way of comparing things in a curved space. The key point, as far as technical details are concerned, is the fact that when written in terms of connections and specifically in terms of Ashtekar connections, general relativity looks like a gauge theory. Gauge theories are theories of particle physics, and we know how to quantize them.
Abhay Ashtekar showed up, and he had called me and said that he had managed to make a complete formulation of general relativity, extending Amitabh Sen's work, because Amitabh Sen's work was wonderful, but it was incomplete. The equations of general relativity are of infinite order. Any power of the fields is involved, and that makes them very hard to study, even classically, but it makes them basically impossible to quantize. When Abhay was done, his form of general relativity had only quadratic equations. So it was a vast simplification. And it was clear to me that that was the way to go. The way to go was to take the toolkit of trying to reformulate a quantum theory in terms of loops of flux and apply it to Abhay's formulation of general relativity.
Lee had, very solid background coming from quantum field theory. He was a student of Sidney Coleman. So, but Lee liked to make big jumps. Carlo was very interested in these foundational questions. They had very different personalities in some ways. It was a very extremely pleasant sort of clicking together that occurred at the workshop. And then it continued. It has continued all these years.
Carlo and Abhay became very good friends, and in fact, for some time, the three of us were quite close. I guess it's kind of emotional. Carlo and I have some similarities. We were both came out of left wing of politics. We were the generation below the generation that had made the great resistance to the Vietnam War and begun the feminist movement and the ecological movement. And so Abhay is a mathematical relativist and a mathematical physicist. And he's, at the minimum, the best of his generation at that. There is nobody I know better to take an idea in this realm and make it a precise mathematical idea. I'm the opposite. I was trained as an American elementary particle theorist by particle physicists who emphasize intuition. Carlo has some of both of our strengths. He's at least as good as me as a physicist. He's a fabulous physicist. And he also has an easier time than I do speaking the rigorous language of mathematical physics and working with Abhay.
Lee Smolin and Ted Jacobson made a step which turned out to be crucial, which is they found some solutions of the Wheeler-DeWitt equation rewritten by Abhay Ashtekar with the new variables. And these solutions were very mysterious because there was one solution for every loop in space. So you start with space, you draw a loop, and then there's a mathematical technique from this loop to have a solution of Wheeler-DeWitt equation.
At that stage, the ideas being proposed in loop quantum gravity still used a background structure known as a lattice.
One day I was talking with Ted, and we wondered what would happen if we just took the lattice away and had these quantized flux lines of Abhay's variables just moving around in space without being stuck on a lattice. And so we wrote that down, and we tried to apply the Wheeler-DeWitt equation, because since there's no time outside the universe, the Wheeler-DeWitt equation says you take a quantum state of the gravitational field, you act on it with a certain operation, you're supposed to get zero. And we plugged in these lines of a quantized electric flux and discovered that as long as the lines didn't intersect each other, if they were closed loops or knotted or braided, we got a solution to the Wheeler-DeWitt equation just like that, and we got an exact solution, not an approximate solution, which nobody had ever dreamed was possible. But we had, it was literally took 10 minutes. So all of a sudden we had quantum geometry in front of us. That was a wonderful moment. So we had solved the Wheeler-DeWitt equation, but there were 3 other equations that you had to solve to make a quantum theory of gravity. They are called the diffeomorphism equations, and they express the idea that there's no preferred observer, there's no preferred coordinate system in space. We couldn't solve the diffeomorphism equations with the same variables that we use to solve the Wheeler-DeWitt equation. When Carlo showed up, I was convinced that the problem was impossible and we were stuck. Then I looked at Carlo and I said, for some reason, do you like to sail? And he said he did, and I was just learning to sail. So we went and sailed and talked about his girlfriend troubles and my girlfriend troubles, and we started to become friends. We really bonded. Then he disappeared for 3 days, and on the next day he came into my office, took off these new jackets, because he was always freezing in America, and said, I've solved all the problems.
Instead of starting from a space and a connection, write the quantum theory directly in terms of linear combination of these solutions of loops. And we immediately realized that by doing that, we could solve the full set of formal equations of quantum gravity. We were not describing excitations that move in space, these loops. Those were the excitations of space itself. We were describing space-time as a collection of threads.
If you look at a two-dimensional surface, like the shirt, for example, right now, then from a distance, it looks like a nice smooth continuum. But if you look under a magnifying glass, you will quickly see that it's really woven by one-dimensional threads. So similarly, the idea is that the raw geometry in this room is really woven by one-dimensional quantum threads. And what are these quantum threads? These quantum threads are fundamental excitations of the gravitational field. So they are not loops of object, but they are the loops from which geometry emerges.
John Wheeler got very excited with loop quantum gravity. He wrote to me in his very emphatic style he always used, with a lot of wow. I still have his little letter on my office on a wall, because of, for me he was the great hero, the great intellectual hero. So receiving a letter for him, excited about my work for the young kid I was more than I could ever dream. I came to Princeton with a piece of a little thing which I made with a lot of key rings attached to one another, which was supposed to give the idea of the three-dimensional structure of space-time. And when John saw it, he jumped and said, yes, that's what I was always been thinking. And he came with his book and a picture in his book. Look, it's the same thing.
It's a quantization of general relativity. So unlike string theory, it's not a different theory than general relativity, which might have something to do with gravity or general relativity in it. It is general relativity as given to us by Einstein, as modified by Abhay Ashtekar, and then quantum mechanics using ideas that were brought in to study gauge theories by Polyakov and Wilson and other people. But it is just the quantization of general relativity.
We realized that loops had some technically were inconvenient, and therefore the loop representation is really not so convenient to use and to get the interesting properties from it and so on. So we introduced, instead of loops, what is called as graphs. So loops are, so to say, closed curves, whereas graphs are objects in three-dimensional space, for example, in which has nodes and they are links, and they can have many, many configurations. And it turned out that the same ideas that were underlying the loop representation can be carried over with the same integration theory and so on to graphs, and then several of the technical problems disappear in this particular way. And so in a certain sense, it is really true that the loop representation is a misnomer for what is being done in loop quantum gravity, or loop quantum gravity is a misnomer, but it is very similar to what is string theory. I mean, string theory is a misnomer because originally there were just strings, but then people realized that there are also other extended objects, membranes and so on, and strings are no more fundamental than other objects. They are all on the same footing, so to say. But since it was called string theory, it is still called string theory.
As loop quantum gravity was being developed, a student of Smolin's, Bernd Brueggelmann was given the task of applying loop quantum gravity to the theory of the strong nuclear force, quantum chromodynamics. But in doing so, he discovered the work of Anthony Trias and Rudolfo Gambini.
And then one day he came to my office with a look of horror on his face and he said, "This has been done before." I was shocked. I was embarrassed. I was pissed off at myself and fate and everything. So it wasn't only our discovery. And it was just a few years before Carlo and I had invented this technique. I wrote them a letter. They had an address in Barcelona, and said that I was very sorry that we had developed this technique in quantum gravity and the Ashtekar variables, and we just had not known of their work. I actually wrote a physical letter. And Rodolfo says, "What are you doing tomorrow?" So he said, "We'll be there," and he hung up. And they went downstairs, got in his car, which is a little sports car with the two of them, and they drove from then, that was the afternoon, overnight, from Barcelona, across France, across the Alps, to Trento in north of Italy. And they arrived the next morning. Gambini, very quickly after that, began to work with a young Argentinian physicist, Jorge Poulin. And the byline of Gambini and Poulin they've done many things together.
During the 1990s, a key breakthrough in loop quantum gravity was made: how to calculate the values of the area and the volume of the discrete chunks or atoms of space.
We did that in the middle of the 90s. It was another super exciting period, and it was the other moment of great collaboration and enjoyment with Lee Smolin. Lee was in Italy at the time. Lee and Abhay were often coming to Italy. We would work together. And when Lee came one summer, it was 95, I think, we just realized we could do that. In fact, this is an idea by Lee. He came and said, "We can do this calculation," and we plunged into it, and of course we did it wrong at some first moment, and then we corrected it. And that's the moment in which we realized that the mathematical solution of this spectral problem, this diagonalization of the operator area and volume to compute the discreteness, had as a solution Roger Penrose spin networks.
I think it was in the early 50s when I had been worrying about various things that maybe space in a small scale would be discrete in some sense, and also quantum mechanical. And also, I remember I was a good friend of Dennis Sharma's, who used to drive very fast and run his car, and if you got thrown to the side, he said, "Well, that's the action of the fixed stars." So the idea was that the inertial frame was determined by distant things. So we used to talk about what happened if you removed all the stars, then would you lose your feeling of inertia or something, or would the car determine your frame? And then suppose you took the car to pieces and took all the atoms away. And I thought of the extreme case where there were just two particles left, both of which had spin half. Now you see, in the normal description, you'd have a quantum mechanical description would you'd have a direction. The wave function would determine a direction. The spin would be about that direction. So you'd have different cases like that. But the idea was that you wouldn't have any concept of direction. You just have, the only thing you would know would be the total spin. So if you bring these two spin half things together, they could make a spin one thing or a spin zero thing, depending on whether they're one way or the other. And there were probabilities involved. Then I thought, well, suppose you bring more particles together, and so on. And then there's the question of how do you know whether the probabilities come from the directions of their spin, in a sense, or does it come from something just because you don't know? I mean, the probabilities is all you're going to get. When you bring these together and take them apart and so on, you only get, the final thing is you'd have a great network of these. Think of them in sort of time. You have these particles coming together, and this one comes together with that. And all you know is the total spin value. So this was a way of trying to make a discrete model, which is purely quantum mechanical, purely combinatorial. You didn't introduce any complex numbers or any differential equations or anything like that. It was just counting loops and assigning values to the loops. But I think there were a lot of things in spin networks which could have been explored more, and I was glad to see that the loop quantum variable people did pick up on this, or they used the theory in a rather different way from the way I'd originally intended, but it's interesting to see these differences as well.
And Lee took a plane, he went to Oxford to talk to Roger, because we were confusing whether we should put a plus or a minus there. I remember a phone call with Lee, and I asked Lee, so what did Roger say? Is it a plus or a minus? And Lee, with a sort of sad voice, said, well, Roger said it doesn't matter, both are okay. And clearly he was not understanding the answer, nor was I. And then, of course, we came out with the technical difficulties, we clarified that. And this is technically, I think this is the major success of loop quantum gravity, because there's a precise prediction of the discrete values.
While Roger Penrose was not directly involved in the development of loop quantum gravity, it's no surprise that his ideas were influential, not least because Abhay Ashtekar, on the recommendation of the great physicist Subrahmanyan Chandrasekhar, was one of Sir Roger's postdocs.
I'm sure he came with extremely good recommendations, or else we wouldn't have taken him on. And he obviously fulfilled these recommendations. And I was very impressed with what he'd done.
Chandra felt that the place I should go to was Oxford, and that was to work with Roger. So Chandra actually apparently wrote, Roger told me this much later, a letter completely unsolicited for me. I also, then after Chandra told me this, I actually applied to this position. And then, eventually I got a telegram from Roger saying, offering you a postdoctoral position. Do you accept? And I didn't know what it meant, because I was a poor graduate student, and in any case from India, there was no way to get any money from anywhere. So I called him, and Roger, of course, didn't know what the salary was. So I said, is it enough to live on? And Roger said, yes. I said, okay, I accept. So that's how I came to Oxford.
In the 1970s, Stephen Hawking and Jacob Bekenstein had shown how to calculate the entropy of black holes. But this was based on the assumption that space is continuous. 2 decades later, loop quantum gravity researchers began to wonder if the formula could be recovered from the principles of a discrete quantum spacetime. After some preliminary studies which revealed pieces of the puzzle, the full computation of black hole entropy was presented in a landmark paper by Ashtekar, Baez, Khorichi, and Krasnov.
And the idea is very simple. A black hole has a surface, which is a sphere, and the quantum state of the geometry are loopy, so are little lines that punch the sphere. And on any punch, there is some degree of freedom. When I say degrees of freedom, I mean the independent ways in which something can move. And you just count this degree of freedom, and the number of them should tell how many degrees of freedom there are on the surface of the black hole, which correspond to the geometry of the horizon. So the horizon is a sphere, but it's not exactly a sphere. It's a sphere that can move, fluctuate, and these fluctuations are degrees of freedom that sits on the surface, and you can count them. And in the classical theory, they're infinite, of course, because geometry is smooth, so you can do arbitrary small fluctuations. But in loop quantum gravity, there's no continuum geometry, it's discrete geometry, so there is no excitation smaller than the scale of the minimal scale of the geometry, which is the Planck scale. So you can count the number of fluctuations on the geometry, and the counting of degrees of freedom correspond to a calculation of the entropy.
When we do loop quantum gravity, there is a certain ambiguity in quantization. This is not uncommon. There is a similar ambiguity in quantum chromodynamics, the theory of strong interaction, which is called the theta ambiguity. And so theta is a free parameter in quantum chromodynamics. It has no classical analog, and its value is determined experimentally. So similarly, there is an ambiguity in loop quantum gravity when you go from classical theory to quantum theory, and it is called the Barrau-Immirzi parameter. If there was an experiment by which I could measure the smallest area gap, I would know its value, and the theory would be determined, and I would be happy. But this is far beyond any technology. We don't even know how to think of such experiments today. Since the quantum of area depends on the Barrau-Immirzi parameter, the number of microstates depend on this parameter. And we just blindly put this parameter equal to the value that is needed to get agreement with the Bekenstein-Hawking formula. This requirement fixes the Barrau-Mirzi parameter, but I did it just for one black hole, and now one can ask the question about any other black hole, and one finds that the leading order term is again the same. So in that sense, there is a check on this Barrau-Mirzi parameter and this area gap. More recent work in cosmology is also giving checks on this area gap, and therefore indirectly on the Barrau-Mirzi parameter. We can leave this as a free parameter and determine it using one of the two methods, and then check if it is true in the other.
Loop quantum gravity is not the only theory to have success in the field of black hole entropy. String theorists also claim to be able to infer this formula. But one of the key differences highlighted by loop theorists is the background-independent nature of the theory.
You do quantum gravity not by having a space and physics on this background, but rather by doing the quantum physics of space itself. That's background independence, very simply. String theory developed as a background-dependent theory, so developed as on a fixed space. In recent years, there have been a lot of effort to bring string theory into a background-independent language. In fact, in some sense, the ideology of string theory has come much closer to loop quantum gravity in recent years. It's a very beautiful idea, string theory. It's a very courageous attempt. I think it has not delivered.
A lot of beautiful things have come out of string theory, but the project of making a theory of nature on string theory is, in my judgment, basically stuck.
The dreams of the 80s have not come true. Nobody has been able to compute the parameters of the standard model, nobody has been able to derive the groups of the standard model, and so forth. In fact, the few predictions, so to say, of string theory have been disappointing, because one sort of prediction in which most string theorists were very convinced of was that if there is a cosmological constant, it has to be negative. Then the cosmological constant was measured and it turned out to be positive. And the other prediction was that we were supposed to find supersymmetry at low energy, at LEP or LHC, and it did not come out. This doesn't mean it's necessarily wrong, but I think it's, as a research program, is losing ground.
String theory comes in an infinite number of versions because it has to have these extra dimensions, within there being an infinite number of ways to tie up the extra dimensions. And so there's a huge problem of empirical content or predictivity.
String theory really, at a fundamental level, appears to require supersymmetry. And in loop quantum gravity, supersymmetry or higher dimensions or a negative cosmological constant are not at all necessary.
Loop quantum gravity is not claimed to be a theory of unification. It doesn't offer a specific way to unify gravity with the other forces and unify them with the different elementary particles the way that string theory, at least initially, was thought to provide such an insight into unification.
Loop quantum gravity is far less ambitious. I personally think that we are not at the point of writing the theory of everything. We don't know probably a lot about the universe, and maybe there are other fields, other particles, other whatever, we don't know. So we better do one problem at a time. And the problem of the quantum aspect of gravity, it's a well-defined problem. We have a lot of information about it, so we can write a theory just about that. And loop quantum theory is a theory about that. So it's a quantum theory of gravity. And I would say it has happened the opposite of string theory, because in the 80s, when we started, there were a lot of unclear issues and things that seemed very hard to go ahead with. And it has progressed in the 90s and at the turn of the millennium and in this first 20 years of the new millennium, more and more and more. And each big problem has been solved.
A frequent criticism of loop quantum gravity is that the theory can't specify the dynamics of how a system evolves.
One way of breaking the definition of a theory, especially a quantum theory, is to separate the kinematics and the dynamics. The kinematics is everything you can measure. The dynamics, how things move. One still finds this comment, loop quantum gravity, one doesn't know how to write the dynamics. But this was 25 years ago. There is some criticism about loop quantum gravity, which keep bouncing since I was a kid. Oh, no, well, I was in my 30s. And people just haven't read the last 25 years of literature.
For full general relativity, I don't have a general solution of Einstein's equation. But let me go to a physical problem, like a spherical black hole, then I know what the solution is, or a certain cosmology, then I know what the solution is. And so loop quantum gravity has done the same thing. And concrete proposals for dynamics have been made, have been verified, have been checked in many, many ways in these models.
And I think today the loop quantum gravity is in a good shape. There is a theory, we know the basic equations. We know that in the classical limit it gives general relativity. We have a lot of indications of that. Is it the right theory or is not the right theory? And for that we need to apply it.
In order to determine if loop quantum gravity is right, it has to make novel predictions about nature, which are confirmed by experiments. And perhaps the most stunning application of loop quantum gravity has been to the very origin of our expanding cosmos, the Big Bang.
When it was first put forward, and also studied by people like Lemaitre in detail, the Big Bang was really the beginning of the universe. Now I think the working cosmologists of early universe think about the Big Bang as really the time at which the universe became hot. So it is a time at the end of inflation, if say for example in the inflationary scenario. During inflation era, people don't often emphasize this, one is using quantum field theory at zero temperature. Big Bang is really a prediction of general relativity in a regime where it is not applicable. Martin Bojowald was a postdoc who had come from Germany and from Aachen, and he had done his PhD thesis precisely on cosmological models on the classical side, a little bit of quantum side, but mostly classical side. And so he really knew the mathematical background very, very much. So he took up this problem and he did some simplifying assumptions and found that in fact the Big Bang singularity was resolved.
So the current expanding phase of our universe is in fact just the continuation of a previous phase in which there is a contraction and then an expansion.
As you evolve back in time, one reaches a point of maximum density.
So this is what we call a bounce. The universe collapses and bounces back.
One of the problems of Bojowald's work was that the bounce could occur when the density was far too low to be realistic. By 2006, Ashtekar, Pavlovsky, and Singh made a key breakthrough, showing the bounce only occurs when the universe is close to the Planck density.
I thought it was too good to be true, so to say. That it is something that is, and I wanted to be very, very careful. So the question was whether this was an artifact of our specific choices. For example, the choice of state we made. So we varied states, still keeping them peaked, but we changed states. We changed various things in the computational models. I kept asking 1,000 questions to the postdocs who were doing the simulations to make sure that nothing was slipping us. But the prediction remained robust in all these things. And after about 8 months of these checks and rechecks, we decided that we should write it up and publish it, and that's what we did.
If there is a bounce, if there is a contracting phase, how can we check this? We expect this to leave a signature in the CMB, in the cosmic microwave background.
At the big bounce, you are in a very strange state. The universe still has some curvature, and therefore your initial conditions for perturbations are not the same as in the usual model. And this might change the spectrum, that is the shape of the perturbations, and this could be seen in the future experiments devoted to CMB.
The observations have certain anomalies. The standard inflation predicts what is called as power spectrum, how much energy there is per unit frequency.
The power spectrum tells you how much power you have in the fluctuations as a function of the L multiple, which is the inverse of the considered length scale. So intuitively speaking, big L, large L, means small scales, and small values of L means large scale. So if you have a power suppression or excess at small L value, it means that you have a power suppression or excess for very huge distances in the universe.
This power spectrum agrees with the standard inflationary predictions for suitable potentials, such as the one that was put forward by Starobinsky, for example, very well at small angular scales. But at the largest angular scales, it does not.
Because these effects correspond to the largest scale in the sky, these are also the ones on which we have most uncertainty. So there is a competing effect between the uncertainty coming from the observations and the effect that we are predicting. So this makes the research particularly hard. But predictions are there, and maybe with future observations we will be able to look at the details.
At the moment, the happy situation is that loop quantum cosmology has some predictions at low L's. These are compatible with the power suppression, for example, of observations. But we also have predictions for other observables, which is called the electric polarization correlation function, electric polarization and temperature correlation functions. If in fact observations, for example, falsify one of these predictions, then we'll re-examine what is happening. What went into this prediction is two things. One is, of course, the basics of loop quantum cosmology, and second is initial conditions. And to me, of course, the most fragile things are initial conditions. And so one would have to go back and see, are there some better initial conditions? To me, these are very well motivated in some fundamental aspects, but of course, they are not compulsory.
For a long time, mathematical theories of quantum gravity remained rather far removed from experiments. It's exciting that loop quantum cosmology has provided a concrete bridge between fundamental theory and observations. Contributions from several young researchers, especially Aguillot, Nelson, and Gupt, have been vital in this process. In addition, younger researchers are also pursuing other directions. And although these are not yet fully formed and therefore speculative, they lead to fascinating new ideas.
In general relativity, we can test the assumptions because we compare the theory with the observations in a regime where we know how to test it. In quantum gravity, we cannot just compare with the real world in the regime where the theory is useful. Therefore, you have to guess what are the correct assumptions. And at this point, nobody knows which assumptions are legitimate and which are not. So depending on the assumptions you make, you end up with a different loop quantum cosmology effective theory. So we have the same mother theory, but we don't have the same effective theory to describe the universe. One path has been followed by Abhay Ashtekar and his colleagues. I follow another path, and in this specific framework, then we find a disappearance of time. We cannot know if this is real, but it is extremely exciting because it has been postulated in the past, for example, by Hartle and Hawking.
In one of our previous films, we discussed the Hartle-Hawking no-boundary proposal, which is often associated with a beginning of the universe. But as we saw in the film, there is a real and imaginary time component. The beginning takes place in imaginary time, whereas in real time, like in loop quantum cosmology, there is a bounce.
So I know that Abhay is not a big fan of this idea of disappearance of time and appearance of a four-dimensional space. But I think it is worth being considered because this is a possibility. For sure, this is not demonstrated and this is not a very hard consequence of loop quantum gravity. But it is something that would be so fascinating with huge experimental consequences. So in my opinion, it should be considered and calculation should be continued.
So it doesn't matter how you do it. No singularities can form in the early universe, so there will be no Big Bang, independently of how you construct your quantum cosmological theory from loop quantum gravity. So whether it's a symmetric, asymmetric, or some other kind of oscillations, but still some kind of bounce should be there.
You come from the past and you can predict the duration of inflation. You know, inflation is the expansion of the universe just after the bounce, huge expansion. So you have a clear prediction, thanks to the bounce, on the duration of inflation, and this could be experimentally probed. To me, this is highly reliable and very interesting because you don't have that in the standard cosmological Big Bang model. From the observational viewpoint, we know that the minimum number of e-faults should be around 60. And we end up with a value which is of the order of 100. 100 is above 60, so this is good, otherwise the model would be excluded, but it is not much above. So this is very good news for testability.
There are more things that we can do to check the big bounce. So there is the possibility to have access to effects that comes from the universe before the bounce. So Aurélien Barrau, with his collaborators, recently has pushed the idea about the possibility to observe gravitational waves that comes from explosions from objects that were present before the bounce.
If the universe did not begin at the Big Bang, does that mean that the universe has always existed?
What about even before eons and eons before? We just don't know.
There could be a past history of the universe which is infinitely long.
An argument against an eternal universe is that we would never get to now if the past stretched back for eternity.
These arguments to me seem a little bit like the arguments that were used by neo-Kantians in the early days of general relativity to say that general relativity is absurd, because in general relativity, matter and energy curve space-time. But how could it be possible? Because you were to talk about matter and energy, one needs space-time. So how could it curve space-time? And very serious people argued this, very philosophers argued this, and I mean, we know that this is completely vacuous argument. I mean, it's not that there is space-time first and then that curves, but everything comes together. So similarly here, I don't see what the argument is. There is actually a detailed prediction of how we got here, and that's it. I mean, so
the way I've heard it expressed is, well, suppose you were to start a race, and I'm going to start my starting gun, but I'm going to wait for an infinite amount of time before I shoot the gun. You'll never start the race because you have to wait for an infinite amount of time. So we never get to now because we have to wait an infinite amount of time.
Right, but there is no gun that is started. I mean, the statement is, I mean, there are many philosophies. For example, in Buddhist philosophy, the universe is eternal, and they have no problem. In fact, they emphasize that, and that the universe cannot have finite beginning. So these people will just say that, well, I just dismiss it because, I mean, the statement is there is no gun.
Another reason for thinking the universe began with the Big Bang are singularity theorems that show that the evolution of the universe cannot be pushed indefinitely into the past.
Of course, there are the singularity theorems, but you can always interpret them as telling you that a quantum theory of gravity should not have one of the hypotheses that you are using to formulate this theorem.
There were some initial singularity theorems that were proved quite some time ago by Penrose, Hawking, and Garrosh and others, which made some assumptions about the kind of matter that sources gravity. In the inflaton that is used in inflation, these conditions are violated. And therefore, there is some hope that perhaps in inflationary models, there is no initial singularity, no Big Bang singularity. But a theorem proved by Bordet, Guth, and Vilenkin showed that this is not the case. Even if you don't make any restrictions on matter of the type that were made before, but if you assume that the universe was always expanding, even in the past, always expanding, then they proved that there is inevitable Big Bang type singularity. Now this conclusion is evaded in loop quantum cosmology. Initially, the universe is contracting and it expands only after the bounce, and therefore the assumptions that they made is violated.
A new singularity theorem proposed by Aaron Wall uses concepts from thermodynamics to argue for a beginning.
Wall is assuming that some version of second law of thermodynamics is really fundamental and should be a fundamental ingredient in this series which determine whether there will be singularity or not. And I agree with that. I think that it really is something that would emerge in approximate sense in a semi-classical regime.
Whether our universe began to expand from a bang or a bounce, there still remains the mystery of why did it have such a low entropy state?
I think we can gain much clarity if we realize the fact that entropy is not an absolute concept. In fact, it's a relative concept.
Entropy is really counting the number of microscopic configurations which lead to the same macroscopic configuration.
When we look at the system, depending on the way in which we interact with it, we can associate with this system different entropies.
Carlo Rovelli has a very interesting view of entropy as something which is not purely objective, but which is somehow related with the way systems interact one with the other. So, clearly stated, it would mean that the entropy of the universe was not low at the big bounce. It means that it appears to be low for us as living creatures. For sure, it's not a social construction. I mean, the entropy of the sun does not depend on the fact that you look at it or not. Still, it depends on the way microscopic systems interact one with the other. So it's not completely subjective, but it's not either completely objective, because the way you couple to another system depends on the kind of system you are.
In one of our previous films, Sir Roger Penrose proposed that dark matter may be related to the remnants of black holes in the pre-Big Bang universe. Penrose dubbed these remnants Erebons after the primordial god of darkness, Erebos. Such black holes may have a large volume, even though they have a small area. And this can be used to explain the low entropy condition at the bounce.
If I look from the outside, the universe seems to be so small, and there are not a lot of ways in which things can be arranged in such a small space. So this is a way in which we say that the universe had a very small entropy. But if now I can describe the universe as a whole, including also the interior of these Erebons, of these black holes, then there is a lot of space. There is a lot of way in which I can rearrange things. And then the entropy of the universe is just whatever. It's not special, it's not particularly low. It's only low if I am a special observer that sits outside of these black holes. I can only probe the physics associated with the exterior of the black holes.
When we look at the oldest light in the universe, the cosmic microwave background, we find that it is not low entropy, it's high entropy. So the low entropy condition of the universe must be in gravity rather than matter. And this brings us to another possibility for explaining the low entropy at the bounce.
What we need to consider is not just the entropy of matter, but also entropy associated with horizons, so to say the gravitational entropy. In the contracting branch, because the dynamics is different from Einstein's theory, a horizon develops, but it grows extremely rapidly. And in fact, therefore, the entropy really grows extremely rapidly. And as usual with black hole horizons, this entropy dominates completely the entropy of matter. Therefore, the entropy is really growing very rapidly, but then at the bounce, the geometry is such, which is non-trivial statement, is such that in fact the area of this horizon becomes infinite. And then after that, the horizon simply disappears. So if you like, what one has to do is to reset the entropy clock in a certain sense at the bounce, and then the entropy again increases. With the scheme that we have, precise scheme we have, the entropy is always increasing towards future.
So there's no reversal of the arrow of time at the bounce like in some models?
Right, there is no reversal of the arrow of time.
In one of our previous films, Alex Vilenkin argued that a contracting universe was unstable.
We have absolutely no idea of what exists in the universe before the bounce. So it's very speculative and very difficult to decide whether the situation is stable or not. And even in the case where the situation is unstable. Usually what it means is that the simplifications we use in standard cosmology cannot be used anymore. But you know, nature doesn't care about the fact that it is hard to calculate. So when we say that something doesn't work, most of the time it means that the model we use to describe these things doesn't work anymore. For example, you cannot use the Friedman equation because the universe is so inhomogeneous that the Friedman equation is not usable anymore. So what? The universe doesn't care that we have to invent another equation. I think the correct way to think is not to go from the past to the future, is to start from what we know. What we know is what we see around us today. The universe is expanding. We have stars, we have galaxies, we have gravity. We have a theory. And then we go backward in time and we see what happened. And in our theory, when we go backward in time, we do not end up with a singularity, we end up with a bounce.
String theory seems to predict the existence of a huge multiverse. And it's often said this can solve the problem of why the constants of nature appear to be fine-tuned for life. But many in the loop community are skeptical of the multiverse. So how do they deal with the problem of fine-tuning? One solution, given by Smolin, is called cosmological natural selection. We'll detail that in a future film. But other alternatives are that fine-tuning itself is an illusion, and that the constants are set by necessity.
They could be necessary, I mean, in the sense of, I agree that all the detailed arguments, it's a hard subject, but all the detailed arguments people do is always keep this n constant the same and vary this, and then look, something will go wrong. But that is never going, so there's no small perturbative solution around us, but that there is no other solution is not obvious to me at all. There could be, all constants are different, and yet life forms. I mean, that to me is not at all impossible.
We have to be very careful in the way in which we treat probabilities. So when you say something is probable or something is improbable, it's with respect to which sets of events, which set of things, which set of possibilities. You are imagining that there are many universes. I imagine that we have only this universe.
And people say, yes, but if the constants were a little bit different, there would be nothing. And that's incredible intellectual arrogance and stupidity, because nobody would be able today, from the standard model, to predict chemistry and life. Nobody at all. So how do you know what would happen if you change a value of of a constant? Imagine you change the mass of a quark, a coupling of the Higgs a little bit. Of course there would not be carbon, there would not be stars, but there would be something else. And nobody's able to say correctly and plausibly and credibly that the universe would not be complex and whatever, because we're not able to do these calculations.
One example of fine-tuning that loop quantum cosmology directly addresses is the initial conditions for inflation.
In general relativity, the question is actually ill-posed because the answer depends on the time that you choose to ask the question. If the initial conditions are specified at a given time, is it highly probable or very low? Probability is very low that the inflation would actually happen with enough number of e-foldings. In loop quantum cosmology, because we have a bounce, a preferred instant of time, we have an unambiguous answer that almost all initial data specified at the bounce will actually evolve into giving us enough number of e-foldings in the future.
A key difficulty for any quantum gravity theory is how it deals with a fundamental feature of relativity known as Lorentz invariance.
In fact, this is a beautiful story. Lorentz invariance means being compatible with special relativity. Space and time can be translated into each other. Zero time interval doesn't mean anything. The simultaneity is not well defined in special relativity. That was a great discovery by Einstein in 1905, and we're very sure about that. In loop quantum gravity, there's a minimal length, but wait a minute. You move fast and you see something smaller than the minimal length, but that contradicts with the prediction. So people say, oh, it's impossible to have a Lorentz invariance in quantum gravity. And the solution is quantum mechanics. You can have discreteness and continuity at the same time. And the typical example of that is angular momentum. If you measure the angular, if you have something spinning, and you measure the angular momentum in one direction, quantum mechanics predict is either 0 or half h bar or 1 h bar, or 3/4. So it's discrete, okay? But if I turn my head a little bit, the component of the angular momentum in one direction shrinks, becomes smaller and smaller and smaller continuously. So it seems incompatible, the discreteness of a component of angular momentum, with a rotation invariance. Okay? But everybody knows that in quantum mechanics there is a rotation invariance and also discreteness. How does it work? Well, it works that when I turn my head, what happens is not that this shrink, is that you have a probability of seeing this full length and a probability of seeing it smaller, and the probabilities move, but you only see either this long or this long, only the discrete values. That's the answer. So the answer is probability. And loop quantum gravity is compatible with Lorentz invariance in spite of the minimal length for the same reason. Namely, if you have something minimal length and you move fast, you have a probability of seeing it minimal length or a probability of seeing it zero length. You never see it half a Planck length. So it's a beautiful example of how quantum mechanics allows discreteness and continuous symmetry groups to stay together.
So here we are completely in the regime where you have to deal with effective theory. So you really try to guess how the high energy quantum gravity effects will manifest themselves on a very low energy phenomena, because you know gamma rays, it's maybe 10 or 15 orders of magnitudes below the Planck scale. So it is very low energy with respect to the Planck scale. And once again, there are different guesses. So if you see nothing, as it is the case up to now, you cannot conclude, because it's perfectly possible that Lorentz invariance is indeed preserved by loop quantum gravity. But in the case you see something, you see that the speed of light depends on the energy even in vacuum, then this would be probably a smoking gun for quantum gravity. Maybe not for a specific theory of quantum gravity, but for the idea that space is not continuous and that you have some atoms of space like you have atoms in a crystal.
If loop quantum gravity predicts the existence of space-time atoms, where do the new atoms come from when the universe expands?
Well, that's the same question as asking in classical general relativity. The universe expands and the volume increases. So you can just ask the question, what creates this volume? Well, it's dynamics which creates this volume. So there is no conservation law for volume, and there is no conservation law for the number of atoms of geometry.
Another route to exploring experimental testing of the theory comes from nature's most mysterious objects, black holes.
A few years back, we have detected for the first time gravitational waves directly, thanks to the LIGO antennas in the US and the Virgo antenna in Europe. And what we are basically seeing is the coalescence, the merging of two black holes, and then the relaxation of the big black hole coming from that. And the way this big black hole is losing its energy through gravitational waves might depend on quantum gravity corrections. So it is still speculative at this stage, but it is possible that some quantum corrections outside the horizon of the black hole change these relaxation modes of the black hole, and this could be probed by gravitational waves. There are similar ideas in string theory, with of course different consequences, hopefully, but it's very exciting that we now think about possible ways of testing quantum gravities thanks to gravitational waves, because the way the black hole moves tells you something about the proper modes of space-time in itself.
We got convinced in recent years, and we're trying to convince the community, that when you go to the center, it doesn't end there, the universe. You continue. You continue, you go through a quantum region, but very rapidly you go out of this quantum region, and what you have on the other side of the quantum region is very simple, it's just the time reversal of what went in. And the physics is simple. If you take a ball, you let it fall, it goes down, and what happened when it hits the ground? Well, the first approximation, it just comes up. And how does it come up? It's exactly the time reversal of when it went down.
The way in which these effects are manifested, as we know from quantum cosmology, is in the form of an effective repulsive force. So this collapsing phase should evolve into an expanding phase.
And why it bounces? Well, because you cannot compress things too much. I mean, there's a limit in compression. Or if you want, there is a Heisenberg uncertainty principle. For the same reason, an electron cannot be squeezed in an atom. You know, classical theory predicts that an electron is going to fall on the nucleus of an atom, but it doesn't. Why it doesn't? Because of quantum theory. Quantum theory forbids something to squeeze something too much. What happens is that the matter bounces, but seen from the outside, this bounce takes very, very, very long time. So the physics, if you fall in, is vroom, vroom. You go to the minimum and you bounce up. But seen from the outside, you see these things in some sense slowing down, takes billions of years, and then slowly coming up. I'm convinced that what a black hole does is go through a quantum phase, becoming the time reversal of a black hole, which is called a white hole, and bounce out.
So what do we need to do to test this idea that a black hole evolves into a white hole?
What we need are black holes that are old and small enough to be exploding today. So this means that we need what are called primordial black holes. Black holes that formed in the very early universe.
I remember Francesca calling me and said, well, you know that this fast radio burst. I had no idea what it is, fast radio burst. So she said, look into that. And so I Googled fast radio burst. And it turns out that there was an article in Nature said the biggest mystery in astronomy. So what's the biggest mystery in astronomy? Apparently they're seeing these very violent signals with a radio telescope. They were seeing Australia and Arecibo. And they were so strong that they didn't believe them at the beginning.
We have too many explanations today. We have more explanations than the number of actual detections.
We had this idea that perhaps fast radio bursts are exploding white holes.
For gamma ray bursts, we know now that depending on their duration, they probably have different physical origins. So it could very well be that fast radio bursts do not all have the same origin.
There are so many radio sources in our universe, so many sources of radiations. So how can we distinguish radiation coming from exploding black hole from all the other sources?
With Carlo Rovelli and Francesca Vidotto, we try to make a full phenomenology of the phenomena that could take place due to those bouncing black holes. So it's correct that fast radio bursts could be explained. I have also shown that the Fermi excess, that is the too many gamma rays we see from the galactic center, could also be explained by this model. But you know, this is not very convincing, because when you are a theorist and you have a model, you can basically explain nearly everything. We know how to discriminate between this model and all the other models that are currently available. And the reason for that is that the redshift dependence, that is the way the signal coming from bouncing black hole depends on the distance at which the source is, will not be the same for our models and for all the other astrophysical or particle physics models.
If I have a burst coming from these exploding black holes, I can put them on a graph in which I have their observed wavelengths and their distance. And this would form a line. Instead of forming a line as all the other astrophysical objects, they would form a curve that is flattening for higher values.
It would be fantastic, because it would be a genuine quantum gravity phenomenon directly observed in the sky. There's a lot of if in this story. The main if is whether a black hole explodes when it's large or when it's small, and we don't know. It's recent stuff, so ideas change. But I'm pretty convinced that the bounce from a black hole to a white hole, which was our main idea, that's solid. If it happens at the very end of the evaporation, what comes out is a black hole, but the black hole, sorry, it's a white hole, but a white hole which is very tiny, and this can stay there for a very, very long time before it dissipates all what is inside and come out. And these are the white holes that, if they existed in a previous eon, sort of before the bounce, before the Big Bang, might have gone through the bounds. A couple of students of mine did calculations which seem to indicate that no, it's very improbable that they explode when they are. We compute the probability of explosion as a function of time. And their first calculation is that the probability is too low, too small. So it becomes high only when the black hole shrinks down to small. Now, it's a first order calculation. We have to go next order. We don't know how reliable it is, but it goes the other way. So we're in the middle of this. Whether it happens when the black hole is large, and then it might be connected to the fast value burst, or when it happens when it's very small. And then the hope to detecting it is through these remnants and connecting it to dark matter.
The reason of the discrepancy, of the debate, of the controversy, is about the stability of the bounds. And it's true that the bounds can be made more stable if it is not symmetric. But it will not change the energy of the emitted quanta. So as far as observations are concerned, you don't really care about knowing if the bounds is symmetric or not. The key point right now is how much time does the bounce take. It might be less than the edge of the universe for some light black holes, or it should be much more for the very same black holes, depending on the assumptions.
Recently, we have worked out a rather speculative idea, which is the possibility that something goes through the bounds. This cloud of small black hole remnants might go through the bounds and constitute a part, or maybe a large part, of dark matter. I'm just mentioning this idea is speculative, it's new, it's not tested, but if it works, it would be pretty good evidence of a bounce.
Any kind of matter content will be destroyed by the bounce. This is obvious. In my view, the only two things that could survive the bounce are gravitational waves, because they are very weakly coupled to matter, and black holes. So black holes and gravitational waves might survive the bounce, and there might be footprints of what happened before. There are interesting mathematical developments that show that it is possible. There are exact solutions of the equations of motion, for example, with a bounce and black holes. So it is possible that they survive. Do they really survive in real life? It's extremely difficult to say, because we don't even know what was the matter content of the universe at this time.
Loop quantum gravity is one of the most exciting prospects for a quantum theory of gravity, and it may well be on the verge of experimental testing. These impressive advances have occurred thanks to sustained creative contributions of several hundred researchers, including Barrau, Tiemann, Veradarajan, Lewandowski, Barrett, Friedel, Dietrich, Giesel, and many others. So what comes next?
We have a foundation of loop quantum gravity that is very solid. We have control about the fact that whatever the shape of the theory will be in 10 years, some things will not change. The discreteness of the area, the volume, and so on will not change. The fact that curvature is bounded will not change. So we needed to use this information to make predictions, to study the phenomenology. At the same time, of course, there are open questions also in the mathematical aspects of the theory. And I think that so far it has been underappreciated, the fact that there is a beautiful mathematics related to group theory, with Chern-Simon theory, with the quantum groups and so on, that is really very interesting to develop. So I hope that both mathematicians and astrophysicists will get more and more interested in what we are doing, and will try to help us to develop the theory in both directions.
Loop quantum gravity has been around for more than 3 decades. And while it has made impressive advances, there is still, of course, the possibility that it is wrong. So how does it feel to risk so much time and effort without knowing if it will really pay off?
There are very few times that a theoretical physicist has the opportunity to be part of starting an area, starting a research program. And if loop quantum gravity, if we don't yet know that it's the right theory of quantum gravity, we know something absolutely marvelous, in my opinion, which is that it's the way that the world might be. It's been an enormous privilege to have the experience of being part of the adventure of loop quantum gravity. And I'm grateful to everybody involved, Abhay, Carlo, Ted, Louis, and all the others. And then I'm also so just amazed by all the young people who come in and so brilliantly develop the subject. So it's the privilege of my life to have had the chance to be involved with this, whether it's right or not.
Sometimes I ask myself, well, why didn't I work on some more concrete problem, which I could see the yes and no in, but you know, life it was it is. And if all the work I've done in my life will turn out to be significant for understanding nature, I'm super happy. If only a small part or nothing at all of it, well, I'll still be happy. Less happy, but still be happy. It's been a fantastic life with working with friends, trying to discover stuff, investigating nature. It's great fun, and we have to try. There is no alternative than trying.